This one for all my peeps that pass. God bless they rest. And check it out. Now I'm paying cause it's mad real.
Yo, it's time for Carnegie Mellon University's Future Data Systems Seminar Series. This seminar is made possible by Google.
All right, guys, let's get started. It's a new semester, and we're super excited today to kick it off with Dr. Russell Spitzer, who is a principal engineer at Snowflake working on Iceberg. So the seminar series this semester is about Iceberg and Iceberg-related systems in the overall ecosystem, understanding how these systems work and how they're all put together and how people are using them. So we went big and got one of the main guys working in this space, Russell. So we appreciate him for being here, and also appreciate him doing this with his wife impending birth of his second child in days. So we appreciate him taking time out to talk with us about databases. That's how important databases are. As always, if you have questions for Russell while he's talking, please unmute yourself and say who you are, and feel free to ask questions at any time. And that way Russell's not talking to himself on Zoom for an hour. Again, Russell, it's a huge deal you're here. Thank you so much. The floor is yours. Go for it.
Yeah. Well, welcome everybody. Hi. Welcome to an extremely technical overview about how Apache Iceberg planning implementation actually works. Subscript in Java. I'm only going to talk about the Java implementation right now. And the reason that I care so much about this is that this is a really crucial problem, and it's something I spend a lot of time thinking about. But before we get into the details of that, a quick overview of who I am. So I'm one of the Apache Iceberg PMC members. If you're not familiar about how Apache projects work, the PMC is the Project Management Committee. So it's basically the people who have a vote in the direction of the project. I'm also a member of the Apache Polaris PPMC, which is the same thing, but for incubating Apache projects. I've contributed to a lot of different Apache projects over my career. I currently live in New Orleans, and I work for Snowflake. And like I said, the reason we're all here and the reason why planning matters is we want to read less data. Regardless of whatever optimizations we figured out about vectorized execution engines, about crazy shuffle algorithms, whatever we can do will never beat out the fact that the fastest way to do a query is to read as little data as possible to solve that query. And we've got a bunch of approaches to doing that. And the quickest one is to use metrics that are associated with your files to try to determine whether or not a file is relevant to your query. So for example, say I have a file. Now there's a lot of different file formats out there, but almost all columnar file formats, like Apache Parquet, have these metrics at the bottom of their file. And we'll basically say, in this file, I have several columns. I have some schema, and those columns have min and max ranges. And with that information, I can then decide whether or not I have to read a file based purely on those ranges in the query that I'm trying to run. So, for example, if I want a query where x is 2 and y is greater than 4 and z starts with BAZ, I can check the metrics in the footer of this Parquet file and basically say, oh, well, 2 could possibly be in this file because it's between 0 and 10. Is y greater than 40 in this file? No, never going to happen. I know for sure I don't have to read this file now. And then just for good credit, can a file or can a row that has Baz starting here? Well, it can't because Z has between A and F, so there's possibly a BAZ string somewhere in there. And I can do this for a whole bunch of different queries. Like if I have an in clause, I can basically play the same game. If X is in 4, 24, and 30, even though I know 24 and 30 aren't possibly in this file, I know 4 might be. So I can say, yeah, potentially I have to read this file and actually check to see if that row is there. And just one more example, I can say X is less than 50 and Z is donut. Both of those could possibly be here because X less than 50, well, 0 and 10 are all less than 50, so possibly have a hit there. And Z equaling to donut, well, D is in between A and F, so there's a possibility that a string donut is in this file. Now, at a file level, this is pretty great because I can just read this footer of the file and know whether or not I need to read it. But the whole point of the metadata formats and the table formats that have come up is that we can probably do better than this. Because the way that these systems were all originally designed is that we're on some file system where checking the footer of a file is like super cheap. We're talking about things like the Hadoop file system, HDFS. Doing a footer check is really, really cheap. I can do it very low latency and pretty effectively. The moment we move to cloud file systems, things like S3 or Google Cloud's version of that, we can't do that as efficiently anymore. We're now charged per API call. So suddenly what used to be a relatively commonplace and simple thing, listing files, checking their footers, is now extremely expensive. And especially if we have to do it over and over and over again. So because of that, we moved to the world of table formats, and Apache Iceberg as one of those. So what we're going to talk about today is basically how Apache Iceberg gets those metrics, puts them in a format that can be read without reading all those file formats, and how we plan queries with that metadata information. So here's a quick overview. We're going to start by talking about what Apache Iceberg actually is, how it's architected, some of the key features that are required to know if you want to get into how planning actually works. We're then going to take a query, pretending that we're in Spark SQL. We'll talk about how that query gets broken down into things that actually go into the Iceberg library. We'll then talk about how those predicates and things that we extract out of the SQL query get applied to manifest list filtering, which you'll know all about manifests after we talk about what Iceberg is built. We'll then talk about how manifests are then filtered. And finally, we'll talk about how deletes, which are a relatively newer concept inside of Apache Iceberg table, then get planned with those data files and tie the whole thing together. And then finally, I'll give you a brief hint of some of the things we're working on in the Apache Iceberg community for V4 of Apache Iceberg. Currently on V3. But we're looking in V4 to change some of these structures that I'm going to go over today pretty foundationally to hopefully speed things up even more in the future. So to give another overview of what we're talking about, we're basically going to be in 3 different lands. We're going to start in this engine-specific land, because all the code we're talking about is basically how do we get a query into Iceberg? And that's going to be dependent on the engine that you're using. So for example, you could be using Spark, could be using Trino, you could be using Snowflake, my employer. You're using one of these systems to write some kind of query in some language, and that language then has to be converted into entities that the Iceberg library actually knows how to work with. And at that point, we can then use those constructs to actually perform a query completely within the Iceberg code base. And then finally, get a bunch of file scan tasks where we actually read some kind of file from disk. And then at that point, there's actually even another layer of filtering where we can actually filter out the row groups themselves. I'm going to skip that part in this talk here because that's, again, file format specific. But basically, the same lessons that we're going to learn about in the filtering of manifest lists and manifests apply to file row groups as well, but again, in a format-specific way. So Parquet works a little differently than ORC, that works a little differently than Avro, and so on and so forth. So let's start at the beginning. What is Apache Iceberg? I'm not going to go through the entire setup of what Apache Iceberg is, how it works, and its history. I'm going to try to highlight only the technical concepts that are important for you to understand how planning works, which means I'm going to constantly be glossing over things and saying, this is an abridged version of this. I'm only cutting out like a ton of things here. I'm going to skip some details that are very important, but are not actually relevant to how planning works. Now, at its core, Apache Iceberg is what we call an open table format, which the definition I like to go with is basically how do we treat a bunch of files like it's a relational database? Because at the end of the day, we basically want some way to separate compute from storage, still have ACID transactions, and then get a whole bunch of other things that we can do in a relational database with just a bunch of like Parquet files. So basically concepts for schema evolution, partitioning. Like I said, we want to be optimized for this cloud storage, and we want to make sure that at the end of the day, this definition of how you work with this table is in itself an open concept that we want everyone to be working on together, people from various vendors, various engines, all working to make sure that it's interoperable. So that's basically, in a nutshell, what we're trying to do here. And the way we do this, and the way that almost all table formats do this, is we have a bunch of data files, and then we build on top of that some set of metadata. And you'll see between the different table formats and different ideas in this space, that metadata is some accumulation of statistics from the data. It's possibly a bunch of files. It could be entries in a relational database. There are a lot of different ways to do this, but Iceberg chooses to do this in a series of files. And the way that that's actually laid out is done in something called the Apache Iceberg spec. So the way that we keep this all kind of vendor agnostic, engine agnostic, is that the Apache Iceberg project starts with this specification, where you basically have to write out the rules for how you interact with an Iceberg table. So you can go to this website whenever you feel like it. You'll see a very long document where we basically go through all of the concepts of how an Iceberg table actually has to work. And what's exciting about this is, as you go through it, you'll see that there's really nothing engine specific or really even that language specific. We do have a few things tied to serialization that are tied to Java isms, but basically the definitions here are supposed to be broad enough that if you come to this spec from any perspective, you can basically build an implementation in your engine that can read an Iceberg table without using the library that we have. Now, the library that we write for this is in Java and does follow all of these rules, but that's not supposed to be a necessity, so that people coming in from other languages or other engines can do their own thing and still have something that's completely compatible with how Apache Iceberg tables work. And the way that we lay this out starts with something we call a metadata file. And this is basically just a JSON description of a table. It's got a bunch of fields and entries. We're going to go through some of them later. But the main thing to know is that it's got the schema and things that describe how the table is generally shaped. And that metadata file is going to list several snapshots. And those snapshots all point to something called a manifest list. A manifest list is a list of manifest files. And a manifest file is in turn a list of data files. So this is things like Parquet files that are actually a part of our table, and also delete files. So our data files are then listed underneath this, and delete files as well. And we basically have this whole hierarchy tree here, where if you ever want to check whether you need to read the layer below, you can look at the statistics in the current file. So this trims down the amount of files we actually have to read to plan something significantly, because we can go through our manifest, which has statistics about our data files, and then use that to determine whether or not a data file actually has to get read. And the details for how we actually do that is what we're going to go through today in this talk. Now, because I wanted to get a few other features in here before we go into the details, I'm going to first talk about quick how commits work here. So like I noted previously, the Apache Iceberg structure is basically this hierarchical tree. You start out with a metadata.json file. It points to a manifest list, which points to manifest, which points to data files. And the way that you do a commit is that you have this pointed to by a catalog, which is another system. So for example, you can use a Hive Metastore, or you can use DynamoDB, you can use all sorts of things as basically a lock here. But it essentially ties a table identifier to a metadata.json file. And when you want to transition between one state and another, you simply build a new tree. So for example, I would write a new metadata.json file, which points to a new manifest list, but also points to the old one because my previous snapshot is still available for time travel, so I can point to that previous one as well. And then that new snapshot, or that new manifest list, points not only to the old manifest, but to the new manifest with the new data files I'm adding. And I basically keep growing this tree sideways as I shift my catalog from metadata.json to metadata.json. Now, the quick thing I wanted to point out here is that this description of how Iceberg works is a little bit old. So this is how catalog plugins, which Iceberg works with, function. Basically, a client produces this whole tree underneath and then talks to a catalog and says, hey, I've made a new tree. Can I switch between the old tree and the new tree? And then swaps that pointer. We've entered into a new phase of the Iceberg project, which focuses around something called the REST protocol, the Iceberg REST protocol, which is a way of basically trying to separate some of that logic so that the client doesn't have to know as much about metadata generation as before. So within the Iceberg REST protocol at the moment, the client no longer has to produce this metadata.json file. Instead, it sends a set of table changes to the catalog, and then the catalog actually writes the metadata.json file and swaps the pointer. So this is better for a lot of reasons, and I can go into them later, but the reason I wanted to point this out now is that we're moving that line even further down. So what we've been working on a lot recently is how can we get this to the point where the client really only knows about the data files it's written, and we can rely on the catalog itself to know all of the logic about how a commit is actually processed. So this is kind of the future of the project, but this is my quick overview of how commits actually work and how we're kind of thinking about that. The only important thing here for query planning is to note that each of these metadata.jsons has a bunch of snapshots that it can point to. So one of the very first things we have to do in query planning is decide which of these trees are we actually going into, because the metadata.json has both the current snapshot as well as past ones. Now, there are a few other Iceberg things we need to know about before we go into planning, or else we're going to get into code and everything will be very confusing. The first that I really want to talk about is, like I said, those snapshots. Next, we're going to talk about schema, which defines how the table is actually laid out, what columns and fields are present, and then something called partition specs, which basically describes how partitioning works inside of an Iceberg table. And I'll go through all of those in details. So again, our snapshots inside of our metadata.json are literally a list of JSON objects. Each of those is a snapshot itself, which has a manifest list path inside of it. You'll see inside of this diagram, I hope you can see my cursor here, we have a manifest list field. If we had multiple snapshots, we would basically just have multiple JSON payloads here. Each of them points to their parent. So you never modify a previous snapshot when it has a new child. When you add a new child, it just points to the previous parent. And you'll end up with some kind of structure that looks like this, where as you continue to make new snapshots, they all point to their parents. You can branch between you can branch like between snapshot 3 and 4 and have two different branches that all go to the same snapshot. But this is basically our structure for storing states of the table that are accessible at this time. The next feature that we need to go into is schema evolution. How does schema actually get stored inside of the Iceberg table? And this is really important. And for those of you who have worked with older systems, you may be familiar with systems that use basically what we call a schema on read pattern, which essentially says, when I read a table, I look at a file, and that file tells me what the schema of the table is. Like I basically can determine how my table is populated by looking at the files, or by determining it based on the files that are in the table. And the problem with this, and the problem for schema evolution here, is what happens if you drop a column and then add back a column with the same name? So if you're familiar with older systems, or working with a table that's represented purely as Parquet files, the answer here is that you resurrect that data. If you delete a column, you're basically only deleting a logical representation that column is part of the table. And when you add it back, you're adding back just that name as part of the schema, which means when you then look at a file, that file, when you dropped the column, was still there. You didn't rewrite the file, you just rewrote this table metadata that described it. So you end up with this problem. You can't really evolve schema in these old formats because there's this strong tie between the name of the field in the table and the name of the field in the file. So they have to match all the time. So Iceberg gets around this with something called field IDs. So when we define the schema inside of an Iceberg table, every single field not only has a name, which is basically how this column is visible to SQL. When I refer to this table and I'm looking for a particular column like ID, I look up the name field inside of the schema and I see I have a field named, or a column named ID. But when I actually go to the data file itself, I use the field ID. So the field ID here is 2. And the reason that I want to do that is that my file could be written when I had a completely different schema. So for example, I might have a schema that was written when the table looked like this. It had 3 different columns. One was age, one was UID, and one was data. But the way that I write those in Iceberg is that when I write this file, I map each of those fields within the Parquet file with a mapping of field ID to column name. So that if I ever want to know what column 2 is, or field ID 2 is, I can do that and I can change the name of that column in the table without doing any changes to the file. So for example, if I do a query where I'm selecting ID out of this table, the first thing I do is I look in my table schema, and my table schema says the ID of that is 2. And then when I go to my file, I can just say I'm looking for the file field with 2. I don't actually care about the name of that field in the file. But if I match, I'm only matching by ID. And again, this is really important because now if I want to change the name inside of the table from ID to user ID or back to UID, I can do that without changing the underlying file because all I do is I change the name of the field, not the field ID of the field. So if I have another different file, I can have one written again with completely different names or with different columns, but as long as I have that mapping, I do the same lookup. So in this case, my file actually was written where the column in the file is written down as ID, but the important thing here is that the field ID was 2. So again, I do my lookup where in the table I get ID is 2, and then when I look in the file, I get 2 goes to back to ID. So again, I've disconnected the mapping of the naming inside of the files from the naming inside of the table. And this means I can evolve my schema really easily. So in this case, if I wanted to drop a field and then add it back, the new field would have a new field ID. So even if it had the same name as the previous version of the column, it wouldn't matter, because the way that I actually look up the columns inside of my files is I do that by field ID. So if there's a new field ID, it will never match the old columns, even if they had the same name as my newly added column.
Maybe,
so this is real. Oh yeah.
Maybe get ahead of like how much. Like, can you define like constraints on the schema for a column? Like you have required true, but what about like uniqueness and other things like that? Like things you're eventually for planning you want to push down because you know more about what the data looks like.
Yes. So can we do those things? Not yet. So the initial spec for Iceberg only allows us to do required and optional. So that was our start. In V3, what we've just done, we've added in some new capabilities. One is defaults. So now you can have a schema with default values as well. So if you say if not present, we should return some other serialized value instead. Or we can say that if this value previously was not set, this is the value you should use. So basically we have a way of adding defaults. In the future, we're looking to add further things like constraints on the column and things like that. One of our problems with uniqueness, and I'm sure you'll see this in a bunch of other distributed systems, is doing uniqueness in a distributed system is super complicated. And we tend in the Iceberg format to say, if you cannot do this universally within all the engines that are working with this system, we don't really want to implement it. So uniqueness is one of those kind of tough ones where I think every time we kind of bring it up, it's considered to be too expensive. But again, it's an open source project, so if folks are interested, we could introduce that in the future.
That's right. What about like not the null semantics? Because you have to make that match across the different engines, right?
Yes. So one of the ways that we handle all of our null semantics and things like that is that we actually have this defined in the spec. We say these are the only ways that values are serialized. This is how they're laid out. So every type within Iceberg is not engine defined. They're Iceberg defined. So we say this is an integer. An integer has this many bytes. It has this max bit min value. So you get around the fact that like maybe your system has int 128 and my system has int 32, and that doesn't matter to Iceberg because Iceberg says, I'm defining int. This is how many bytes long it is. This is the min and max value. This is where we'll get to some more interesting things about this later, but basically that's our system here. We have strongly defined types. They are defined for Iceberg. Everyone has to take that and convert to your engine local version.
Awesome. Thanks.
Cool. Moving on. Okay, so the last concept we kind of need to go over is hidden partitioning and partition transform. So this is another kind of complicated thing. So within Iceberg, if you're familiar with how other systems do partitioning, like Hive will partition by basically just making a directory, and that directory will have a column name and then equal to a string version of the value of that partition. So basically makes a directory structure where the files are placed in specific directories, and if you're in a specific directory, that means you have that partition value. Iceberg does this very differently. First, Iceberg says, whenever we write files, we're going to associate a tuple of partition values with that file, and that's based on what we're calling a partition spec, which is a collection of transforms for different columns in that file that produce a value. So the example I've given here is a bucketing transform. So for those who aren't familiar, bucketing is essentially you take a hash of your value, you apply some modulo to it, and you get an integer out. And the way we define this is we say a certain source ID is used as input to this, and we define this transform itself with a certain field ID, so when we write it to files, we know where it is. And we use that then when we produce data files. Writers will use this to make their own files. So in this case, we could have the output of this tuple being 1. We only have one transform, so we take the bucket function, we apply it, we see that it's 1, and then we put files with that tuple associated with them. Or we could get different files where those, when you apply this hash function, you get 2, and we associate them with a different partition tuple. This is independent of the position where the file actually resides in the table. Instead, we need this mapping of what spec was used to make it, and then we can use that to figure out what the tuple values mean. And I note that we are, again, talking about source IDs here because, as I mentioned before, we want to make this name independent. So this is tied to the field ID of the schema entries and not the actual column name. So this, when it says it's working on source ID 2, might be working on a column that we've defined as data, but has a field ID too. But we don't actually use that. We use the source ID when we compare all of these things and connect them back together to avoid renames destroying other parts of the table. So when we rename a field, we don't actually have to change our partition transforms. They remain exactly the same. So we have a lot of different transforms that we can use. Just a quick overview of them here. One of the ones where I think Andy was kind of noting, how do you deal with different serialization issues? Truncate is an example where this comes very, very complicated, because truncating different types ends up being very difficult when you get to strings and things like that, because you might want to get min and max values of truncated strings. And if you get into something like Unicode, that ends up being actually kind of tricky, because not all code points are valid, so you can't just do like byte-wise truncations and stuff like that. Anyway, the main point I want to have here is we basically have these explicitly defined within the Iceberg spec. So again, we say exactly how you do all of these functions inside of the specification. So every engine that's attempting to find a value after it's been transformed uses the exact same function. So our bucket transform is actually defined as a very specific Murmur3 implementation that is then used modulo the number of buckets you're trying to use. But anyway, all of this is extremely well defined. So any engine looking at this or any implementer can remake these transforms and get the exact same answers given our data types. All right, I know that was a lot of stuff, but I promise all of these concepts are going to come up again and again as we go through how the planning actually works, because we actually have to know how to figure out what our partitions are. We have to know how to figure out what our fields are as we go through all of this. So let's start in Spark SQL, and I'm going to talk briefly about the data source v2 API, but if I went through this entire part of the code path, which exists completely within Spark, that would be another like hour or 2 hours of talking. So we're going to basically say a lot of stuff happens, and at the end of the day, we enter into the Iceberg Spark plugin, which has something called a Spark Scan Builder. This is part of the data source v2 API, but it's basically where Spark talks to its data sources and says, here's the stuff I know about your query. Do something with it and give me back a bunch of rows. So how do we get that stuff that's in Spark and make it into Iceberg stuff? So Spark is going to give us two specific things that we're going to use for our planning. One is in the form of a function called push predicates, which we're going to use to make our Iceberg filter. And one in the form of a function called prune columns, which will give us what information we need to do our projection as we are looking through our files. So both of these get passed into Iceberg code, and they're implemented in a pretty straightforward way. So for example, the Spark API is going to call push predicates on the scan object that it's making inside of our Iceberg code. And it's going to have a bunch of Spark predicates. So at the top of this function, we have this Spark method called push predicates, which takes a bunch of Spark predicates and returns a bunch of Spark predicates. But the important thing to know here is that what we need to do is, with this input, we need to know what we can push down. So the first thing we do is we convert these from the data source v2 expression language inside of Spark into the Iceberg expression language. So that's our convert function, that first line there, Spark v2 filters.convert. The important thing to know here is that the input is a Spark class and the output is an Iceberg class. So our conversion happens there. We basically have a one-to-one mapping. If you have a data source v2 filter that's an equal, we have an Iceberg equivalent equal operation. Once we do that, we then try to see whether or not we can actually push it down. And that's where this fun little bind thing happens, which is the first point in which we're going to get back to why those field IDs are important. So the expression we get from Spark doesn't know what the Iceberg field IDs are, right? It's written in terms of this query. It just knows, hey, there's some X in this table. I need to push down some kind of predicate for it. The unbound predicate inside of the Iceberg code base represents one of those predicates where all we have is a name, we have maybe some literals, and we have an operation, but we haven't actually bound it to a specific schema inside of Iceberg. So when we try to bind it, we can actually determine whether or not this fits the schema that we currently have. So is this a predicate we can actually handle or not? And we do this by looking up the field IDs and determining, is there a inside of our schema, is there a field with the name X that we can bind this particular expression to? Because once we've done that, once we have the field ID tied into the expression, at any point later, we can look at any data file, which may have it bound to a different name, and use that field ID to get the correct column. So we do this little test to see whether or not we can bind it, because if we can bind it, we know we can actually do this kind of metric lookup. And if so, we add it to the list of expressions we're actually going to try to push down inside of the Iceberg API. And the rest of the little fun stuff we do here with pushable filters add and post-scan filters add, that has to do with communicating back to Spark what we were actually able to do and what we were not able to do. The reason that we have that sort of stuff is that Spark has its own optimizations where if you say, hey, I've completely handled a particular predicate, Spark can then say, oh, then I won't reapply it in the compute layer. This is actually well, I'm going to say new, but like new to me because I've been working in Spark since like Spark 09. And for a long time, Spark would just always double compute. So basically, if you had a predicate and you pushed it down, Spark would still apply that predicate again at the compute layer, just because they were like, yeah, we don't know for sure. But this was added in as a mechanism later to say, there are certain predicates we know we can completely evaluate, and there's some that we know we can't.
All right, so the question in the chat, doesn't the API know if the query includes a as of for time travel to pick the right field ID for bounding?
Yes, so that part I kind of skimmed over here. I wasn't going to go through exactly how the snapshot selection works, but yes, there's basically a part of the API that parses out a as of, and that gets set through yet another API and then pushed down into the scan builder. And then when it selects which snapshot it starts from, that's where that kind of gets picked in. So you pick a snapshot. The snapshot has a schema ID associated with it. This is another thing I glossed over. We actually have all of the schemas that have been used in the table in part of that metadata.json. So we use that ID then to look up which schema we should be binding to, which lets us correctly bind to the schema as of that snapshot, as opposed to the current schema. But that's a really good question. I was skipping that part. All right. Any other questions, or should I keep going?
Keep going.
All right. Okay. So how do we do our schema pruning? As noted by the questioner, we actually do have to determine what schema we are looking at based on what snapshot we are loading, but I'm skipping that part here. Basically, we have yet another function called prune, which is going to take in a Spark definition of what columns it wants, the Iceberg schema of the table, and then output an Iceberg schema that matches the requested columns. The only additional important thing to see in this bit of code here, this is in that second block, this.schema equals whatever, is that we have to include the filter expression here as well. Because one of the really important things here is that we may have a predicate that involves a column that is not actually required to be projected by the query. So for example, I could select X where Z is greater than 5. In that particular query, I don't actually project the column Z for reading. I'm projecting it only to evaluate my predicate. So in those cases, I might have to extract columns out of my predicate in order to know that I actually have to surface those columns back up to Spark. So again, at the end of the day, I take a Spark construct, I apply some functions, and I get back out an Iceberg schema that I can use in the rest of my planning. With field IDs again, because we need our field IDs this whole time. So now that I've got my Iceberg specific objects, I have an Iceberg set of expressions, and I also have this Iceberg schema that I want to read to, I can start going into the Iceberg specific code, which means the first thing I have to do is I have to read that snapshot. So as noted before, the snapshot I'm reading is described by another part of the Spark SQL dialect, or you can do it programmatically, but basically that's going to give us a snapshot. And our snapshot is, as I said, associated with a specific manifest list. That manifest list has within it a bunch of data manifests and delete manifests. I'm going to read that file. That's what's happening here in the snapshot.data manifest.io and delete manifest.io. I'm basically reading through that file and getting particular things out of it. There's a cache behind this, so it's not actually reading through the file twice. And I end up with two objects, my data manifest and my delete manifest. And this is all I need to actually pass into my code that actually does the planning. And that's manifestgroup.java, which is where we're going to spend almost the rest of our time talking about how Iceberg does this. which is where all the real work happens and where all the real complexity lives here. So the first thing we have to do once we are reading this manifest list is we have a list of data manifests and we have a list of delete manifests. We need to determine which of those manifests are actually important, because there is a possibility that a manifest only contains entries for data files which could not possibly match our query. Now, the only thing we can do to check a manifest list entry here, a manifest row, is the partition summary. So a manifest list is composed of these rows. There's a bunch of information there, like where this file is. But the important thing for us are two things. One is the partition spec ID, which tells us which set of partition transforms were used for all of the data files in this manifest. And the other is something called partition statistics, which says, for those tuples within this manifest file, what are the min and max bounds of those tuples? And this means that we can actually do filtering for all of the data files within a manifest if we can filter for their partition. So I'm going to go through this a little more concretely because I know this is a little more complicated here. But essentially, we might have an Iceberg expression that says, we're looking for a timestamp that's happened before November 5th, 2008. Now, our partition spec may apply some kind of transform to that timestamp column. So our partition tuple doesn't actually have a timestamp in it. It has something else, like perhaps we were using the day transform. So our tuple doesn't actually have a timestamp. It has a days from epoch that represents the day from epoch of all of the rows within that data file. So I have to take that Iceberg expression and project it and bind it to the specific partition spec that was used for a manifest. And that basically converts my expression from timestamp less than some particular timestamp to the day timestamp field of that partition summary has to be less than the day version of that timestamp, which ends up being an expression that looks like day timestamp is less than days from epoch version of that particular timestamp. So once I have that expression now in terms of the partition summary, I can actually go through all of these partition summaries and check whether or not this expression is true or not. So the way that we do this is something through something called a visitor pattern. If you took some fun Java or object-oriented classes at some point, you'll be familiar with this. But basically, we define some kind of tree structure, and we define how we go through it based on each node type. So in this way, we make a visitor that says, okay, if you reach an AND node, the way to compare an AND node is to look at all of its child nodes and make sure that all of them are true, and then iterate through your child nodes and call the visitor again. So in this case, we would visit and would say, visit all of my children, make sure all of them are true. We would then visit the first greater than would then have a specific implementation to describe how you figure out whether x is greater than 5. You would then visit the greater than again, and then finally you'd visit a starts with, and you would then go to the starts with implementation, which says I need to have some specific way to find z within this partition summary and evaluate it against Baz. And to make this a little more concrete, let's go into one of the actual codes of this, because it's a lot more simple. It's a lot simpler than I'm describing. So we start by basically saying if we have no statistics, well, our rows might match. We might have some file and some manifest within this, some file within this manifest that might have rows that match because we have no statistics. So in that case, we fall back and we just say, you better read this manifest. Alternatively, we enter into this visitor, which will then visit all of my nodes, and on each node do that specific code. So for example, this is the less than node code on the right. And it's pretty simple here. We basically say if in that statistics structure, if its lower bound is less than the literal, then we know that there can't be any matches here, because we know that there are no rows less than this inside of the manifest. Otherwise, we know that there might be some hit, and we then have to actually go into that. Sorry, we know that that part of the expression is true. So basically, we have a version of this for every single operator, which says if the stats.lower or .upper or some combination of the two has some comparison to the literal that we're trying to compare it to, we either say rows match or rows can't match. And again, remember, we have already bound this particular expression into the partition spec, so we know that we're matching apples to apples here. Our literals here are now transformed to match specifically to the statistics that we are trying to compare them to. So once we've done that, we now know which of the manifest files we actually have to open up. But once we've opened up our manifest files, each of those has a list of data files, and we don't want to read all those data files. Again, we need to check for each of these entries within a manifest, do we have to actually open that data file and read the data within it to answer this query? So we can do even more exhaustive filtering on these because, like I mentioned for manifest lists, all of our entries only have this partition summaries. Within a data file entry inside of a manifest, we have a lot more information. So again, a manifest is basically this relational file. It's a bunch of Avro rows right now, which has a data file construct within it, which gives you a partition, which gives you the actual partition used for this data file. There's no upper or lower bounds because you have a specific partition tuple for every data file. We then have, for every other field that we're recording metrics from, the value counts, how many total values are in this column, the null value counts, we have a NaN value count, so I skipped that here, and we have a lower and upper bound. And those are the most important things. So all of this is populated when the Iceberg table is written. So when you write a Parquet file, one of the last things that happens within the Iceberg write path is that we aggregate all of the metrics up for all the different row groups and store that into this entry. So all of these statistics are basically directly extracted out of the footers of all the files that we've just written, but now they're available here as a row in a file, so we don't actually have to look at the footer to get them out. So how do we actually compare all of this? Like I said, we have this nice typed structure for our partition tuple, which matches to some set of transforms in a partition spec. So for example, we might have foo, comma 1, and using that partition spec ID, we can basically say, oh, that was written with the partition spec where we're truncating and only getting the first 3 characters of column var, and we're taking the identity of ID. Again, we're actually doing these all by field ID, but I'm just using names here just to make it a little clearer. And then for our column metrics, we're keeping these maps. And the map is a map of field ID to the serialized binary representation of the min or max value. So this is bad for a few reasons, and this is one of the things we're working to fix in in table format v4. The first is, if I gave you these maps where it's a field ID to binary, can you tell what the type was that was used to serialize this? And as noted before, since we have different schemas in the life cycle of the Iceberg table, we actually can only do that if the type has never been promoted. Because if the type changes, then the representation of the min and max value might change, and we have none of that information here. So that's a little bit of a problem. You'll notice that inside of the spec, we have this whole thing about allowed promotions, where we only allow promotions where we're able to actually look at this length of this binary and determine what the type was. And then one of the issues here is this is also not really great for wide tables. If we're storing tons and tons of metrics here in a map, if you're familiar with how maps are stored in Parquet or other columnar types, the only way to get a particular field out of this would be to read all of the keys and all of the values. They're not stored in a way that's actually push downable within a columnar file format. So maps are also not great if we want to use a columnar file format because we get no push down ability. We can't read only the metrics for a few columns. We have to read them for all of the columns. But this is what we have to deal with right now because this is how it's currently laid out in Iceberg v1, v2, and v3. So when we want to actually compare this, we enter into the manifest reader. So the manifest group, when it begins this filtering process, will then start reading manifests using manifestreader.java. Manifestreader.java has a bunch of initialization code, but eventually you get down to this function called entries, which filters each of our files, each of these data file entries, based on 2 things. You'll see we've got an evaluator here that's evaluating the partition, and we have something called metrics evaluator, which is evaluating the file class as a whole, and it's actually doing all those column metric comparisons. So our first partition evaluator here is basically using a class called evaluator.java. Evaluator.java takes an Iceberg expression and evaluates a struct against it. So that's why we use that there. And then we have this other class called inclusive metrics evaluator, which we use for evaluating all of those different serialized maps of min and max value, which has the code to do that. Basically, it says, given an Iceberg expression, do we have some way of actually determining whether or not the metrics held within this file are valid? And again, we return either rows might match or rows cannot match. We're never making a decision that rows definitely exist, although we can do that for partitions, but we still don't do it. We're always saying either these files need to be scanned by the engine or they don't need to be scanned by the engine. We don't ever make a strict determination that there will be a correct row. So the way that our partition evaluation works is, again, we have another visitor. So basically, we have an expression visitor, which, similar to the one we saw before, has a definition for each of the different operations. We take our Iceberg expression, we bind it to this particular partition struct, and then with that, we then run our evaluator, which will basically just do the exact same thing as we saw before, but with a little more complicated extraction, because now the way that our expression is written and the way the struct is constructed might be slightly different. So we use an evaluator to extract out the proper part of the struct that we're matching to this literal value, and then we check whether or not it's less than 0. But again, we're basically doing a mapping here of names to field IDs to make sure that everything lines up correctly. When we're doing column metrics, we are basically doing the same thing. We have taken the stats object out of this data file, and we're going to check the various stats that are within it against the Iceberg expression. So here's an example of greater than. We start by checking our nulls, because we can check if we contain only nulls. We can check if we contain only nans. If so, we know that there's no rows that can match because you can't be greater than those. And then if not, we actually check our upper bound. So there's a lot of magic baked into this line where T upper equals upper bound of term. This is a place, again, where I didn't want to go into the strict details here, but basically the different types of terms we have. So we can have a function, we can have an actual column value, we can have an actual metric, can all be defined differently here so that we can actually use this same logic against, say, a generated column or an actual column in the table. So there could be an expression that we need to apply to this upper bound before we can compare it to our literal, or we might be able to use it raw if we're actually checking the value of the column against a literal. Anyway, the long and the short of it there is we, again, are just basically comparing that upper bound inside of the file struct to the upper bound in our expression. And if it works out, we say the rows can match, and if it doesn't, we say the rows cannot match. And we put those all together, and then we end up with an answer for a particular file of either rows might match for this file or rows don't match for this file. Okay, so once we've done this, we've basically evaluated whether or not a data file has to be read from our engine to actually find rows for this query, except I've skipped one important detail, which is delete files. So Iceberg has this concept of delete files, which basically say, for an existing data file, I'm allowed to mark certain rows as no longer existing. And I'm not going to go into the full details of how that's built out, but basically we need to know if a delete file applies to a data file in our query, because if so, our engine that's reading needs to apply those deletes as it goes through the data file. So we do that in something called a scan task. A scan task puts together both the data file that needs to be read along with the delete files that need to be read with it in order to get the actual data from that particular file. So we do this, again, inside of manifest group. So again, we're doing more work inside of there. All the slides that we've talked about previously populate that term entries that I've linked there as the output of all of our hard work so far. So that's basically all the data files we need to actually process. And then we also attach to it this thing called context.deletes for entry, which I haven't talked about at all before, because when did we ever talk about delete files? Well, the only time we did was way at the beginning when I mentioned we have some delete manifests that we need to read. Now, the problem is when we initially implemented deletes, this came in V2 of the Iceberg format, we needed a way to associate those deletes with the data files that we were reading, but we made slightly a few complicated ways of actually associating those deletes with a data file. So we have a slightly complicated mechanism for associating them back once we've got our data files we want to read. So we have this thing that we call the delete file index. Now, the delete file index is made from the delete file index builder. The delete file index builder is initialized at the exact same time that we initialize our manifest group with that list of all of the delete file manifests that we need to read. When we do all of our configuration to put various filters onto our manifest readers, reading out our data files, we do the exact same thing to our delete manifest. So basically, everything you do to a data manifest, we do the exact same thing to a delete manifest. We check its upper and lower bounds, we check what partitions it's in, and we end up with a list of only the deletes that are applicable to a particular set of files. And at the moment before we start actually planning our data files, we build this index. So right before we start going through all of our data files, we're basically ready to assign all of the appropriate delete files to each of those data files as we build our scan tasks. At the end of the day, basically, we have built up a set of maps. Now, by partition, we have made up a map of all the equality deletes, all of the position deletes, and then we have this last fun thing where we're just mapping the position of the path of the data file to a specific position delete. And the reason for that is that we've recently introduced the ability to associate delete vectors with specific data files. You can also do this with position delete files, which is another concept that I don't want to go into the detail of. But basically, it's another way of looking up what delete files are relevant for a specific file. So inside our delete file index, when we call for entry, it's just going to go through those maps and basically determine what is the correct set of deletes for a particular data file. Since we're running a little bit low on time, I'll go over this just kind of briefly. The first thing we do is we figure out if there's any equality deletes. That's what happens in the first two lines of global and equal partition. Those lines are basically saying I'm looking for any equality deletes, so it might apply to this data file. The only way we can do that is either we have global equality deletes that apply to every single data file, or we have ones that apply to files in a specific partition. The other argument to those functions, sequence number, is something that I've purposefully skipped talking about here, but it's a Lamport's clock that basically says when files were added, and we use that to determine whether or not these delete files actually apply at this particular snapshot. The next thing we do is we look for delete vectors. That's a new thing in V3. You can only have one delete vector for one file, so finding them is very quick. But if you don't have delete vectors, we have to check for these things called position deletes, which is another type of delete that we add, which is essentially a parquet file, which has a list of rows and paths, and you have to associate those paths with data files, and then the row identifiers that you get there are the ones that you have to delete. So you basically get like, out of data file A, delete row 1. Out of data file A, delete row 2. Out of data file A, delete row 3. So you basically get a row for every row that you're removing. Delete vectors are different. It's just a bit set, which is the rows that you're going to remove. All right, so once I have all of that, I then do one final step before I give my beautiful scan task back to the engine to actually do work. And that's, I have something called plan tasks, which is in table scan util, which is basically a way of saying I might have a defined split size. I only want to read a certain amount of data in a particular task at my engine level. And you can actually specify that to the Iceberg API. And when you do that, it will basically take multiple scan tasks and either split them up because they're too large, because the data file is too large, or combine them because the data files are too small and you want to read more data in a specific Spark task or something like that. So once we've done all that, we're ready to go. We can basically take our task, serialize it out to Spark, and then there will be Spark-specific logic to take this information about a data file and a Parquet file and read that into a Spark-specific memory format. But we've completely done all of our planning, and at that point, any files that get to Spark have to be read by Spark, with the small caveat that if you have limits or things like that, you can potentially terminate before reading all of the tasks that have been planned for you. Now, a few notes on this. I've skipped a bunch of things, but hopefully this has given you at least a very high-level picture of how this actually works, along with the actual code and places you can look to learn more about how it's actually built. But the big caveat for all of this is, one, not all engines use all of this code path. Some only use the planning part and do not use the task part, the task building part. Others skip this entirely and just build their own implementations from the spec. And the slightly bigger sad note is that we're planning on changing a lot of how almost all of this works. So what are we trying to do in V4 of the Iceberg spec to make a lot of this information I just told you no longer relevant? The first thing is that we're looking to expand the way column stats are stored. So as I mentioned before, we are storing them right now as these maps, which are not very good for columnar types. And they're also untyped, so we actually don't know what they were written as. So that makes type promotion basically impossible inside of the Iceberg format for anything other than type widening. And the other big thing we're looking at is removing manifest lists entirely. So one of the things you might have noticed is that almost all that logic we're doing to deal with a data file is an expanded version of what we're doing on a manifest list. So the question has been raised, and the proposal is out now by me and a bunch of other people in the community about why not we just make the manifest list itself just another type of manifest? Because it already has all of this logic for basically comparing column aggregates and this logic for dealing with partition transforms. We might as well just make that logic universal and have a manifest that points to more manifests. Additionally, one of the things we want to do is say, what about all of those child manifests? In the current setup, there's basically a lot of churn, because whenever I want to change one of those child manifests, I basically have to delete the whole file and write a new version of that file with the new rows in it. What if instead I could also apply delete vectors to my metadata? So basically I can start deleting things out of my metadata without actually removing and rewriting those files. So there's two big new things that are coming that will throw into turmoil a bit of the stuff I'm working on. The stuff I've described today. But the key thing that's going to probably remain the same is the way that manifest evaluation works. We're just going to expand that concept to work with even more things. And it hopefully will not have a special set of logic then where manifest lists get treated completely differently than manifests. So those are some big things happening in V4. I don't want to keep everyone super late. So my last thing I'd like to shout out to everybody is the Apache Iceberg community is an open source community, open governance. Anyone can be a member. Anyone can work on the project. And I encourage everyone who's paying attention here, join us. We have a dev list that's very popular. We have a personal Iceberg Slack that you can join off of our website. We have tons and tons of community events and talks. Keep attending things like this, learn more about the project. We have GitHub issues that you're welcome to come and contribute to. And I think we're probably going to have another big conference in 2026, and everyone should attend. So with that, Ed, I know I've covered a lot of different things. I'd be glad to take any questions and go into more detail if anyone needs.
My mouse is not working for some reason. So if any questions, I'm gonna just have go for it.
There's a question in the comments.
Let me see if I can load the chat. All right.
Yeah, I can read it too if you want.
Oh, I got it. I'll read it over here. Okay. Where do we get to the first one?
It's just the last question.
Okay, yeah. Is all predicate pushdown first go through partition checks? In the Hive days, docs warn against ever writing queries that require a function that makes the engine unable to skip files using partition values. Iceberg seems to say as long as it knows how to resolve the function callback to the derivative of the partition value, it can still skip files. And the answer is yes. So Iceberg will take any expression that is convertible to something that can work against partitions and do so. So basically, if you do a predicate on timestamp, which is one of the examples I went through, we'll actually take the partition metrics and convert them to match that. So if we only have a day partition, but you do a predicate that's based on the timestamp value, we'll convert that to make the appropriate partition expression. So this is the hidden partitioning part of Iceberg. Basically, you don't have to know how the table was partitioned. If there was a way to take your predicate and apply it to the partitions, we will do so. And like I said before, you can even have your table. You can have your table in tons of different ways, different partitionings, and we'll always use the partition spec that particular file was partitioned as our expression base.
Okay, so other questions. If you want to ask a question, just mute yourself and go for it.
I have a question. There's this thing called Puffin that I heard. Do you know anything about it?
Yeah. So I did not talk about Puffin files in this as well. Thanks, Kevin. Kevin is another member of the Iceberg community, so thanks for joining. So Puffin files are another kind of recent addition to the Iceberg spec. The only thing you have to know about Puffin files for planning at the moment is it's the place where we store delete vectors. So if you're looking into how delete vectors are actually stored in the Iceberg format right now, they're stored within these separate files called Puffin files. Other than that, we can store additional metrics inside of Puffin files that can describe other aspects of the table. For example, the number of distinct values, important things for doing join ordering and stuff like that. But those are currently not actually required for planning itself, but they are surfaced up to engines through other APIs. So the way that Spark handles this is Spark has another data source v2 API that you're allowed to implement, which basically says Spark will call and expects to get back a statistics object. And the way that Iceberg deals with that is Iceberg checks this Puffin file. If the Puffin file has the statistics, it will then return those to the source.
All right, so I guess I'll finish up with my last question. Are there aspects of like the other systems? Iceberg's the dominant one. Are there aspects of other systems like the Hooties, maybe Delta Lake? I mean, I understand Polaris is a rewrite of the Iceberg spec. Are there other aspects of these other systems that you're like you wish that Iceberg would have, and then you eventually want to add them?
Oh, yeah. So, I mean, Iceberg being an open format, we get things from a lot of other places. Just a quick clarification, Polaris is an Iceberg REST catalog implementation, and not an Iceberg spec implementation. But
Got it. Thank you. That's super helpful. Yes.
Yeah. So one of the things I think we've talked about a lot, especially in this, like, as AI is becoming more and more important, we see wider and wider tables because people want to store feature sets everywhere. And one of the most common problems people have with really wide tables and these table formats and file formats is that the way Parquet is constructed, the way ORC was constructed, even though they have columnar representations of your data, so you can read columns as a block, you have to keep all of the column vectors for the same row group in the same file. So that means that if you have 10,000 columns and each of those columns is like, I don't know, 10 megabytes, you only get, or say a row is, I'm getting bad numbers here, but basically you end up with very wide files that have like a single row in them. You have this problem where that means you can't actually get the columnar benefit anymore because your columns, your files are very wide and your columns end up having to be very short so that they all fit in the same file. So there's a lot of different formats that are kind of attacking this and trying to figure out different ways to deal with this. So Lance is one of those. And then there's different table formats that have different solutions for dealing with this, like basically adding, I've been calling them like sister files. So basically you'll have a main file, and then you can also have other files that have additional columns that are for the same set of rows, but are in a different file. So those are concepts that I think are important. And I think that's the thing that I'm most interested coming up soon. But I'm not sure whether or not it's something that should live in the table format itself, or if it's something that should actually be a part of the file format and described there. But watch this space. We have right at this very moment, we have major proposals in the Iceberg community on trying to make the file format part of Iceberg pluggable, which would start opening the door to trying out some of these ideas in an open way. Something that Hoodie does is they let you do these sister files. So you can also like update a file by adding a single new file that just has a new column and basically have it overwrite at read time. This is something we've kind of tried to stay away from inside of Iceberg because I think it ends up being a kind of complicated problem as well to do that merge. And we're a little, the Iceberg community is very focused on making engine compatibility a high priority. So anything that ends up looking like it might be hard for some engines to do, we've stayed away from. So sometimes you'll see features that appear in other formats that we don't have yet, just because we're like, well, we don't know how Trino would do that, or we don't know how Ray would implement that, so we don't want to add that in right away.